Chapter 11 is about problem solving. Problem solving brings together a lot of what we've already learned from the first 10 chapters: concepts, language, images, all of the things that, all of the phenomenon that we've understood now about cognitive psychology can be used to help us understand the basics of problem solving. So, when we talk about problem solving, the first thing we need to do, of course, is define what a problem is. So, a problem is basically a situation in which there is a difference between a current state and a desired goal state. So, you're in a particular situation and you desire to be in a situation that is different, and you have to figure out how to get from the current state to the goal state. That process is called problem solving, the process of developing a solution designed to get you from the current state to the goal state. A very simple example of a well-defined problem is what you see here, a Sudoku puzzle. I've never been able to say that word, Sudoku puzzle. And the state is empty Sudoku cells, and you have to fill in the cells according to the rules of Sudoku. Um, and it's a very well-defined problem. Once when you know where to start and how to finish. Problems like this, like Sudoku problems or problems that you get as homework in calculus or algebra, those are well-defined problems. Problems that have clearly defined goal states and constraints. So the rules are well known. The end goal is well known. So games, for example, playing games like chess. Chess has very clearly defined goals, very clearly defined constraints and rules. Those types of problems are very well defined. And then there's those problems that are ill-defined, that lack a clearly defined goal state and constraint. So for example, what do I want to do with the rest of my life? How do we increase revenue? What's the best way to provide housing for people? There's lots of these types of problems that are ill-defined, where we don't even know what the end state is sometimes, and we're completely unaware of the constraints that are before us. So the first thing you have to be able to do in solving problems is to define them and represent them. If you can't define and represent a problem, then you don't have a problem. There is no problem. Basically, this process involves stating the scope. So what does this problem include? And the goal, what is it you're trying to accomplish of the problem? And then organizing the knowledge that you need for addressing the problem. The mental representation of current and goal states, the roles or constraints, and all of the allowable operations available to solve the problem are things that you need to organize, things that you need to line up and make sure that you're able to get access to. So here we have a very simple example of defining a particular problem. This is a very simple example called the pennies problem. So if you look at the stacks of pennies in stack A and stack B, the question is there a way to move 2 and only 2 pennies such that all of the pennies are touching 3 and only 3 other pennies? Okay, so that's the problem. And you can get to a bunch of different solutions, right? You can try, for example, in the first stack, right? You can try removing one of the pennies, but then you've got a situation where not all the pennies are touching 3. In the other stack, you can try moving a penny around, but again, you've only got some of the pennies touching 3 and only 3 pennies. The solution is pretty simple if you look at it. Basically, the solution is to lift 2 pennies and place them on top of 3 other pennies. And what you end up with is a situation where each penny is touching 3 and only 3 other pennies. The reason people don't see this is because, well, we'll talk about that a little bit later. Here's an example of another problem that you can change. But changing the way you look at it will help you solve it. So here we have this checkerboard. Imagine a checkerboard, and the question is, can you cover each? Can you place dominoes that cover two squares each and completely cover the checkerboard without having any dominoes hanging over the edges or anything like that? Now, if you're looking at this, you're going, I don't know, right? It's kind of tough. But if you look at it like this, right? Look at this. Look at it like this, right? Pretend that you've taken a checkerboard and you've colored it in like like a checkerboard would be colored, and then you have a domino that's half red and half white or half yellow. And then imagine if you were to remove two of the squares. Well, if you remove two of the squares, that means you end up with 30 red squares and 32 white squares. Because remember, a checkerboard is made up of 64 squares, right? So 32 and 32. So if you do this removal like this, you basically you end up with 30 red squares and 32 white squares. And there's no way that you can cover this checkerboard with a two-sided domino with a domino with two sides on it completely uh, without leaving at least one square uh, uncovered. Which basically tells you that this problem cannot be solved. But notice that you couldn't solve this problem by looking at it like this, right? It was much harder to solve it. But when you look at it like this and you realize that those two colors are the same, and that leaves you with an uneven number of squares, 30 versus 32, and each domino is an even number, 2, 2, 2, 2, 2, you realize it's probably not going to be possible to cover all the squares with all the dominoes. The reason why it's kind of hard to see solutions to problems is due to this uh, characteristic called functional fixedness. Functional fixedness is defined is when you focus on how things are usually used while ignoring other potential uses. It's a very common barrier to our problem solving capability. So, for example, the two string problem, right? Um, the person on the left is trying to connect the two strings, but she can't reach both of them. The solution on the right side is where the person gets a screwdriver, attaches it to the string, and then swings it. That makes the string move closer to the person. They can grab onto it and then attach the strings. That's using a screwdriver in a very unusual way. The other example is candle and matchbox. So imagine if you have a wax candle um, and a box of thumbtacks, and your job is to attach that candle to a wall. And so you're thinking about it, and you're like, well, you think maybe can I push tacks through the candle? Nah, that won't work. And the solution is really simple. The solution is basically empty the box of thumbtacks, then tack the box to the wall, and then put the candle on top of the box. And most people don't see that at first because they're thinking, well, that box is only used to hold thumbtacks, and I'm not really gonna, I really think of it in terms of a platform to hold candles. So, what developing solutions to problems? There's a lot of different, ways to go about it. Um, One of them is a trial and error strategy. And this is what a lot of early theories like associationist psychologists were based on. And, essentially it's, it's like trial. You try something, doesn't work, try something, doesn't work. You try something that gets you a little closer, try something that gets you a little closer, and eventually you reach a solution to the problem. Over time you learn new things, you learn how the thing works, and eventually you come up with new solutions. Um, Trial and error works best when there's not a lot of possible solutions. When there's uh, when there is sort of a limited set. So, for example, if you're trying to learn how to write write computer software, a lot of us who have learned how to do that have done it through trial and error. When I was learning how to write Java software in the Java programming language, a lot of it was, I would, type something in and then run it through the compiler and it would bomb. And then I just kept trying and trying and trying, and eventually I would get it. But that's a very limited, in some ways, very limited sort of space, because the solution is the solutions to the different programming challenges are fairly limited, right? There's not an infinite way to do it in a particular language. Compare that with you know how to live a happy life. that's that's a big problem that you probably don't want to be doing trial and error, because there's a lot of possible solutions, a lot of ways to screw up, and you can really mess yourself up before you reach an adequate solution. um Gestalt approaches are where, a gestalt, of course, refers to this holistic view that the whole is greater than the sum of its parts. So it's a much more of a much more of a holistic view than breaking things down into steps in an analytical fashion. Um, and in a Gestalt approach, the solutions arise out of new productive processes. So, you create these mental representations of information and use that to eventually achieve some goal. A lot of times, a solution is the result of a sudden breaking away from past associations. There's this notion of insight. Insight is like a aha experience, like aha, I finally got it, and it's where you suddenly realize the solution to a problem. There's been a lot of research done on as to what goes into these, like, insight moments. You know, you're going to experience them in your university education. There's going to be like certain concepts that you're trying to understand, trying to understand, trying to understand, and then eventually, after banging your head against the wall for a million times, finally you'll go, "Aha! I finally understand it. I get it." That's what insight is all about. Oops, sorry, the wrong button there. Let me go back. There we go. A mental set is a tendency to use the same set of solutions to solve similar problems. So you're kind of stuck, right? You've got this set of solutions that's worked for you in the past, and you're just trying to solve problems that are similar. A good example of this is students that come from high school into university. You're stuck. You try to use the same study strategies, if you did have any study strategies that you used in high school, and you realize those aren't working real well for you in college, especially as you go higher and higher up from freshman, sophomore to junior. You start realizing that you're falling further and further behind. This is where you really need to recognize that, I may be a victim of mental set, and I really should probably start looking for other ways of solving my problems. With analogical transfer, this is where you use the same solution for two problems with the same underlying causes or underlying structure. So the two problems may look different, they may appear different, but in fact, underneath they're both the same problem. Um, you encounter this a lot. For example, if you're a consultant, a business consultant, you're going from client to client to client, And each client is going to have certain business problems that they want you to solve. And one of the things that you do as a consultant is you look at the client's problem, and maybe they're having an issue with uh, process, inefficient processes. Another client is having issues with trying to deal with changing market conditions. And you go to these two different problems, and they look like completely different problems. But as a business consultant, you're like, you know what? Both these problems are caused by the same thing. They're both caused by people that aren't trained well. They don't have the right technology to deploy, and their strategic direction is just not defined very well. So I'm going to go ahead and use my same solutions to help these two separate companies solve their problems. One of the things, for example, here's an example: the nine dot problem. Connecting dots. Connect the dots with four straight lines. Okay, so here you have nine dots, and your job is to connect them all the dots, with four straight lines. So you're gonna sit there and you try to work through it, and eventually, is the solution is to not view the outer dots as a border. So, nobody said anything about there being a border, right? In other words, a line can continue on past a dot. So I draw one line to connect the top three dots, uh, a diagonal line to connect three dots, a line going from bottom to top to connect the dots on the left, and then the last couple of dots I have left, I draw a diagonal line. That's four lines. And like I said, they do overlap. Some of the lines do overlap on the outside of the box, but there's no rule that says they can't. So here's a problem. Imagine that you're a surgeon and your patient has an inoperable stomach tumor. However, one possible surgical method you think might work is to use a beam of radiation. A high intensity beam should destroy the tumor. However, at high intensities, the beam will also destroy the surrounding healthy tissue. How can one cure the patient with these beams and at the same time avoid harming the healthy tissue that surrounds the tumor? So compare that problem to this one. A small country is ruled by a dictator living in a strong fortress situated in the middle of the country, surrounded by villages. Many roads radiate outward from the fortress like spokes on a wheel. A general vows to capture the fortress and free the country. So, how is that general going to take over the fortress given these conditions? Well, the general knows that if his entire army could attack the fortress at once, it could be captured. So you got to get all the troops there at once. But the dictator has planted mines on each one of the roads leading to the fortress. The mines are set so that small bodies of men could pass over, but any large force of men would detonate the mines, destroying the villages. So a full-scale direct attack on the fortress appears impossible. The general solved the problem by dividing his army up into small groups and sent each group to the head of a different road. When all was ready, he gave the signal and each group charged down a different road. All the small groups passed safely over the mines, and the army then attacked the fortress in full strength because they all arrived at the same time. In this way, the general was able to capture the fortress and overthrow the dictator. Now, we can apply that general solution to that problem to the earlier medical problem that we had earlier. So the doctor has radiation beams and the patient has a tumor, but the tumor is surrounded by healthy tissue. So what we want to do is destroy the tumor with beams, but if we were to send one high intensity beam to the tumor, we would also kill everything around it. Which is not good if you're talking, for example, about a brain tumor. You don't want to, you want to kill as little healthy brain as possible. So just like with the fortress, With the fortress, you can't send the entire army down one road. So what the general did was he sent little small armies down little individual roads leading to the fortress, and that's the solution to the radiation problem. Rather than sending one high intensity beam at the tumor, you send lots of little lower intensity beams at the tumor, all aimed at the same spot. Each one of those individual low intensity beams doesn't doesn't do much harm, but when they all group together at the site of the tumor, they can come together and burn out that tumor. So one of the things that we talk about in problem solving is this notion of a problem space. A problem space basically is your problem, a statement of your problem along with all of the possible solutions and conditions. Basically, just everything you need to understand the problem and solve the problem. A couple of the things that you find in a problem space that are related to the solutions are what we refer to as algorithms and heuristics. This is a very basic fundamental distinction that applies to a lot of different areas, not just cognitive psychology, but also computer science, decision science, lots and lots of other branches of knowledge uh, use these terms and these concepts of an algorithm and a heuristic. An algorithm is like a recipe. It's a prescribed, laid out problem solving strategy that always leads to the correct solution in problems with a single correct solution. So it's great for those types of problems where you only have one correct answer. So working a Sudoku puzzle, for example, you can come up with an algorithm to solve that puzzle because a successfully completed Sudoku puzzle only has one solution. Any math problem that you get in class, if you're taking a math class, any math problem you get, only has one correct answer, and and you can create an algorithm or a list of steps and instructions for solving that particular problem. It's like a recipe, recipe for baking a cake or instructions for, putting together an IKEA piece of furniture. Those are all algorithms, step by step procedures, step by step instructions for accomplishing some goal, for solving some problem. On the other end, we have what are called heuristics, and heuristics are not step by step instructions. What they are strategies. And they're strategies that don't always necessarily lead to a correct solution. They're basically rules of thumb, general guidelines that you would follow to deal with particular problems. So for example, a heuristic is a classic example of a heuristic is do unto others as others would do unto you. That's a heuristic. That's a general strategy for trying to live a good life. There's heuristics for diagnosing problems. For example, if you're a crash investigator, doing research on what caused a particular jet airliner to crash, you're not there's no algorithm for that. It's basically just using a bunch of your experience and a bunch of your prior knowledge to figure out what went wrong and piece together things. You're using heuristics that are based on the evidence that you see, and those heuristics that are based on the evidence, if you follow them, they should eventually lead you to identifying the root cause of an accident. So a classic example of problem space searches is the Tower of Hanoi. Basically, how can you move the disks to go from the initial state to the goal state? So what's the most efficient way to move those disks from one peg to another? This is a classic problem. If you take a computer science class, You will see this. So read the description of this in your book and of the Tower of Hanoi. It's a classic problem. One of the things that you have to do, for example, if you take a computer class, is you have to solve this. You have to write a program to solve this, and there is an algorithm that you can write to solve this in the most efficient way possible. Um, so here's the example, right? So you can only move one disk at a time, but only onto either an empty space or a larger disk, right? So you need to move the blue disk. To move the blue disk, you need to remove the green disk, and to remove the green disk, you need to move the red disk. so so it's a matter of moving the red disk over to an empty space, then moving the green disk over, and and once you do that, this is some of the problem space for the Tower of Hanoi problem. This is going from state to state to state to state as you move each disk, and each one of these little mini pictures here gives you the the state at that particular moment until you get down to the bottom end, to the two squares at the bottom that show you the goal state. But this is a very simple example of a problem that has a well-defined answer, single answer. In other words, I got to get all the guys over to the opposite peg, and it uses an algorithm. There's lots of different ways of solving problems. Lots of different strategies that you can use to go through and solve different problems. One of them is called a means ends strategy, and this basically what this is this involves repeated comparisons between the current state and the goal state. So basically, you've got like where you're at, your as is strategy, and your to be strategy, and your to be your as is condition and your to be condition. And essentially, what you've got there is you're comparing the two and saying, okay, what do I need? What do I need to get me there? Right? What do I need to get me there? So, for example, you might use a means end strategy to say, okay, in 5 years or 10 years, let's say 10 years. In 10 years, I want to, I want to have $1 million in the bank, and I want to have my college degree, and I want to have a house and a car. Okay, you want those four things. All right. So you're sitting here and you're like, okay, I'm a college student. I ain't got no money. I ain't got no degree. I ain't got no car, and I ain't got no house. Right. So it's like, okay, how can I get to that? How can I get to that state? Well, I'm going to start saving money. Okay. So you start saving money. You check yourself back. I've got $500 in the bank. Well, I'm getting closer. Eventually you'll graduate. So you'll graduate. Let's say you graduate and you have $2,000 in the bank and you got your degree. Now you need to get the car and the house. So you work on that, and every now and then you double check and what your status is against what your goals are, and you create a strategy to get you closer and closer to your goal state. A hill climbing strategy involves continuous steps toward the goal state. So rather than doing like a compare and contrast between the end and the goal, what you're doing is you're building steps, planned steps toward the goal state. So if we go back to our goal of saying, okay, I want to have $1 million in the bank, a car, a house, and a degree. You're like, okay, first thing I got to do is I got to get my degree. Right? That's the first thing I have to do. So you work on that. You get your degree. And then the next thing you're like, okay, I got to get a job. Right? So you get a job. Right? That's the next step. Then your next goal is, okay, I got to start saving money. So that's your next step. You start saving money. Then you're like, okay, my next goal is, all right, I got to get good credit. So you start, using and credit responsibly. Next goal is, okay, now I got to save more money. So you got to save more money. All right, I have enough money now to buy a car with a 2-year loan, and it's a car that I can afford on a 2-year loan with low enough payments. So you go ahead and you do that, dang, bang, you got a car, right? So next is, you want to keep saving money. You want to have $1 million in the bank. So you're constantly checking your account. You're saying, okay, I'm going to have at the end of this year, I want to have, $10,000 in the bank. What do I need to do for that? Well, I need to invest, blah, blah, blah. You do that. So it's constantly just making steps moving you toward the goal state. The working backward strategy. This one's probably my favorite life strategy. I use this one a lot, actually. So working backwards is where you start with the goal state and you backtrack the steps that got you from the initial state to the goal state. So you're like, okay, I want $1 million, a car. What was it? $1 million, a car, a house, and a degree, right? Okay, so let me work back. So if I have all of those things, what was the prior step before that? Well, the prior step before that was probably having a really good job, right? Also doing good work, working back, you're going to eventually hit the point where you have to start investing your money and dealing with investments. Working back, you're going to hit the point where, you had to look for a job. So you basically work backwards, um, and, uh, and build the steps that you need, a long-term strategy that you need for getting to the goal that you want. One of the big issues with problem solving is the fact that our uh, ability to solve problems are constrained by our cognitive system. So, attention. One of the things that is huge in problem solving is attention. You need to focus attention on problems. The harder the problem, the more attention you need to focus on. And if you don't have enough attentional resources, you're not going to be successful solving that problem. Just basic energy. I mean, it's been shown that our problem solving capability is greatly compromised when we're tired or when we're hungry. So having the proper resources for solving problems is a very, very big deal. So this is a good example of allocating resources. In other words, focusing, being able to focus resources and experience to solve a particular problem. So this is the matchstick problem, where you write out a math formula using matchsticks or toothpicks, whatever, take your pick. And so the problem is that the formula on the top is written in Roman numerals and it's wrong. So basically it's xi minus v equals iv, which in Roman numerals translates to 11 minus 5 equals 9. And of course, as we know, 11 minus 5 is not 9. 11 minus 5 is 6. So the solution to the problem is pretty straightforward. Essentially, you just like move the solution over. And the solution has to be that you only move one matchstick to solve the problem. And this one's pretty simple, right? You just move the matchstick over to make the IV turn into a VI, which is the number 6, and that corrects the problem. So here's another example. We have 3 problems here, A, B, and C. All of them are wrong. So the A is, 4 equals 3 plus 3. B is 3 equals 3 plus 3, and C is 11 equals 3 plus 3. All right, so we have 3 plus 3 on the right-hand side. On the left-hand side, we have 4, 3, and 11. So how can we solve those? By moving only one matchstick. So here's some of the solutions. The solution to A is like the one that we saw before. And that's pretty straightforward. It's something that we've seen before. The solution to B is not real obvious because it involves a twist, a change of strategy, and a change of, attention. Rather than focusing on the numbers, what we did in B is that we switched the rotated one of the sticks to of the plus sign to create an equal sign, so that we have a correct expression where 3 equals 3. For C, what we did was we shifted the down slanting stick over to create a V. If you look at the previous one, right, that was XI, so we just shifted it over to make a V to create a 6, and so 3 plus 3 equals 6. These are slightly different approaches that require more thinking, more resources, more experience, basically. And if you don't have if you don't have like the mental energy to focus your attention, or if if you're hungry or tired, you're not likely to see the solutions, particularly to B and C. Expertise. So, what defines an expert? Really, an expert is somebody who has very deep knowledge about a particular area. And one of the big areas of research in cognitive psychology is this notion of understanding the difference between experts and novices. Uh, Experts versus novices differ in many, many different dimensions. Perception and attention. Basically, an expert will see things in a problem that a novice doesn't see. An expert will focus their attention immediately on specific aspects of a problem, whereas a novice will waste a lot of their attention going from point to point to point trying to figure things out. Experts are much better at remembering facts about a particular problem because they have convenient ways of storing parts of a problem based on their experience. And experts also are much easier at find it much easier to strategize to solve particular problems. Um, One of the classic examples of this, of experts versus novices, is the research that's done in looking at the difference between chess grandmasters versus chess novices. So, chess, of course, is a very complex game, and the people that spend their lives studying chess and playing in many tournaments can achieve the rank of grandmaster, which is a very difficult thing to do. But a grandmaster versus a novice. Grandmasters look at chess problems, at chess boards, very differently than novices. Grandmasters are able to easily look at a chessboard and memorize the positions of the pieces on the board, um, because they're able to group those pieces into meaningful patterns. Chess masters can strategize 5, 6, 7, 10, 20 moves ahead uh, when they're playing a game, whereas most novices can only see maybe 1, 2 moves at the most ahead. So uh, the differences are stark, and there's still a lot of research going on as to what makes an expert versus a novice. And the reason is obvious. We want to be able to bring experts up to speed as quickly as possible. The world, it would be a lot better if we could have more experts at, say, for example, solving diseases or curing diseases and solving serious problems. um, your book presents kind of wraps everything up into a nice little package. um, it presents you with the ideal problem solving method. This is a very, very useful approach, and I would strongly encourage you to check that out and learn the ideal problem solving method um, for um, for solving pretty much any problem. And each one of those letters stands for a different thing. So, identify, define, et cetera, et cetera. Each one of those steps involves uh, defines a particular part of the approach that allows you to break a problem down into its parts and solve it. The L in ideal stands for learn. And that's really where you take the results of your problem solving approach and learn from it. Basically, say, okay, what did I learn from this? And that's really, really critical. You want to make sure that you're learning about from your mistakes as you go, not only to help yourself, but ultimately to help other people.